As we continue with chapter 7, one thing that you notice right away is that we spent quite a bit of time talking about vision, right? Well into today's lecture. And the book spent a whole chapter on vision and then crammed all the other senses into one chapter. Two reasons for that. One is the reason the book already alluded to, which is that a large amount of cortex is subsumed by vision. Vision is clearly very important. Humans are visual creatures. We make much more use of vision than we make of a lot of our other senses. But the other reason is that vision offered a really good example of how all of this works. And with vision is a very relatively well understood sensory system. You're going to see a lot of stuff is the same old story today, or you already did when you read the chapter in the textbook. Many of these other senses have a lot of things that work pretty much like the visual system, and we'll try to highlight those commonalities as well as some differences. So today we're going to talk about all the other senses, but in particular audition and your touch and taste and smell sensations. So start with hearing. The purpose of hearing is to detect sounds and also to localize them and determine their identity or meaning. So you really want to be able to listen and not just hear. You want to be able to understand content from the sound you hear. Whether that's a person talking to you or a sound that would indicate danger, safety, the availability of a desired resource, etc. So these are things to think about as you think about how our hearing system works, what it's there for. Again, from a functional evolutionary standpoint, all these systems evolved to do some kind of purpose. So you should remember this purpose in terms of understanding how hearing came to be the way it is. So the fundamental stimulus for the auditory sensation is, of course, sound. But more specifically, sound is a wave. Again, we talked in detail about waves last week. So sound's a longitudinal wave. It's a different kind of wave than the transverse waves that light is made up of. And it also consists of a different kind of, its physical nature is different also. Light was a transverse electromagnetic wave, meaning it was composed of electrical and magnetic radiation. Sound is composed of compression and rarefaction. Rarefaction is the opposite of compression, of something like air. So of course, one obvious consequence of this that you're probably already aware of is that sound can only transmit in a medium, right? And so sound doesn't transmit through empty space, for instance. So like, for instance, in space, nobody can hear you scream. That is true. Sound doesn't transmit through vacuum. But it does transmit through air and liquids and solids. And it's a longitudinal wave of compressions and rarefactions. And what that means is that the air is moving apart and closer together, and that's propagating through space. It's composed of 3 dimensions, much like light. So here's a first commonality. So in light, we talked about hue, saturation, and brightness or value. And now we're talking about pitch, timbre, and loudness. And they're analogous concepts. So the pitch, the dominant frequency of a sound, is just like the dominant frequency of light. The timbre, which is the complexity of the sound, is a lot like the saturation. Is it composed of just the one color, or lots of different colors with one dominant color? Is it composed of just the one dominant frequency, or is it composed of a lot of other frequencies on top of the dominant frequency? So that's timbre. And then loudness is the amplitude, which is measured in decibels. And that's a little bit like the value or the brightness. So the brightness was how many photons were there, the density of the photons. The loudness is the magnitude of this compression wave. In terms of the frequencies, so these are the 3 characteristics. Human hearing ranges from about 30 hertz to 20 kilohertz. This high end does drop off over the course of life in particular. And so for instance, in middle adulthood, you probably can't access all of that 18, 19, 20 kilohertz kind of sound. And then that'll get progressively lower. Just for a reference point, if you think about middle C on a piano is 260 hertz, the A on a violin is 440 hertz. In particular, the frequencies up to 2 or 3 kilohertz are really crucial for human voices. And your auditory system is, of course, optimized to be able to hear human voices for kind of self-explanatory reasons. Just to give you an idea, so we talked about wavelengths, right? Like I gave you examples like this table in concept has a wavelength that's defined by its size scale, right? So this is a wavelength. Wavelengths again apply to sound just like they apply to light. But just to give you an idea, we talked about how the wavelength size scale for light was several hundred nanometers, like 380 to 720 nanometers. Now the scale, middle C is 260 hertz, that's a 1.3 meter wave. Or it's well over 1 million times the wavelength of visible light. So these are very long wavelengths in comparison to light wavelengths. And even if you think about 10 times this for for like maybe a couple of kilohertz in the voice range, that's still going to be 130 centimeters then, still a lot more. These are big waves. And that'll be important in a moment. So a few things to know about the physical qualities of sound. So sound is measured in decibels. You've probably heard that term before. What's important to note in this context is the decimal is a logarithmic scale because human hearing has a particularly incredible dynamic range. Minimal sensation is about 1 trillionth of an atmosphere, and the pain threshold is 10,000 atmospheres. So this is 13 orders of magnitude difference. That's a really, really big difference. So, just to give you an idea of scale, like 13 orders of magnitude above the minimal, 13 orders of magnitude above the minimal amount of light that you can see is above the burn threshold, meaning that's bright enough that it'll actually destroy your retina. Like the dynamic range of vision and hearing is much, much broader than many other senses. And so this logarithmic scale is important because doubling the amplitude in a physical sense of a sound does not cause a perception of a doubling of the sound volume because of this huge range. Okay, so here's a graphic of what those compression waves look like. You think about each of these little things as being like a nitrogen molecule in the air, a rarefaction where there's less density of nitrogen, a compression where there's more, less, more, and then this whole thing is moving in space. And it's called a longitudinal wave because it's waving in the same direction as it's moving, as opposed to waving this way. And so it goes, say, from your speaker to your ear, and your ear's job is to transduce this compression wave into neurological stimulus that can be understood as sound. So here again is another picture. So again, amplitude, kind of like the value, the loudness. The loud sound has a big amplitude, soft sound has a small amplitude. The frequency is the dominant frequency is the pitch. This is like the hue. So there's a low frequency and a high frequency sound. And then the complexity, like the saturation, the timbre, simple versus complex. Conceptually very similar to what we were talking about in light. So the ear is the thing that you hear with, and it's both the primary organ for the hearing in the vestibular sense that we'll be talking about. It's commonly decomposed into an outer, middle, and inner ear. The purpose of the outer ear, in essence, is to focus sound. The purpose of the middle ear is to transduce sound from the air medium to the liquid medium. And the purpose of the inner ear is to transduce sound from the compression wave to an electrochemical signal. So you start with sound, and you get this tonotopic place map where the frequency spectrum of the sound is converted to a spatial map. Again, like we talked about the conversion of the frequency spectrum of light into a map across the 3 tones. Now we're talking about a tonotopic map. So a general concept here is this transformation of information from one kind of coding scheme to another. Frequency distribution to place distribution. The outer ear, again, is a focusing apparatus in essence. There's the pinna, which is this convoluted surface on the outer part of the ear. It can be manipulated in most mammals to focus sounds. It's particularly evident if you have cats. So you have cats with ears that point up. You see them rotating their ears. They can rotate one ear at a time. They can do that to focus sound so that they can orient their sound, much like the antenna on a bug. Some humans can move their ears. I can move my ears. It's not really functional. It's a vestigial effect. I can't move my ears in a way that allows me to focus sound selectively, right? So we do still have this kind of ability, some of us don't. But in mammals, this pinna is not only a focusing apparatus, but it also allows for selective focus. The external auditory meatus, or ear canal, is the air-filled passageway from the external environment to the middle ear. The middle ear is separated from the outer ear by, So the middle ear is separated by, lost my train of thought for a second. So the eardrum separates the middle and the outer ears, the tympanic membrane. And inside the middle ear are these three bones that you've heard of, the malleus, incus, and stapes, right? And so this assembly of bones, what it does is it transduces the air wave into a fluid wave. And the reason this is important is something that you can appreciate if you've ever gone swimming, right? Like, you can hear sounds that are being generated underwater when you swim, right? But what happens when someone talks to you from outside of the water? You really can't hear them, right? Most of you probably had that experience. The reason for that is because the sound bounces off the surface of the water. So the sound in the air bounces off the water instead of being absorbed into the water and continue to propagate. That same thing would happen with your middle ear if there wasn't a mechanism. Like when you went from the outer ear, which was air, to the inner ear that was liquid, if you didn't have this mechanism, you'd lose all that information, just like the noise bounces off the top of the water and you're swimming. So that's what the middle ear is there to do. And then the oval window separates the middle ear from the inner ear. And so the eardrum connects to the bones, and the bones connect to the oval window. And then at the oval window, the bones are driving a fluid wave without loss of conduction. Does that make sense? The inner ear then includes the fluid-filled cochlea. It's shaped like a snail. That's why it's called cochlea. It contains both auditory and vestibular apparatuses. And the organ of corti is the auditory apparatus. And the hair cells are rooted to the basilar membrane by Dieter cells, and they extend to the tectorial membrane. And fluid waves, as they're passing through, so it's still got this compression wave moving through space inside the cochlea now. They displace the basilar membrane with respect to the tectorial membrane. So this motion bends hair cells. Again, hair cells are being involved in sensory reception. Now, unlike vision, when the hair cells are bent, you get an excitatory postsynaptic potential. And this is a general concept for all the other senses besides vision, that receptors are excitatory. The vision receptors, again, remember we talked about how they fire when there's nothing present, and light is inhibitory because it breaks the rhodopsin apart. Remember that? So all the rest of them are excitatory. So EPSPs. That's the relevance of that concept that we talked about earlier. Then there's also one more window. So there's the oval window and the eardrum. The third window is the round window. And the round window is there because, in essence, so how to explain this? You can have sound waves in water without the water sloshing around. But the magnitude of sound waves moving through water is very, very small because water doesn't compress. And that's important to know. All liquids are essentially incompressible compared to gas. And so water that's, like if you have a box and it's filled with water and it's totally filled and there's no air in it, sound waves that pass through that have a very small magnitude. What's actually happening in essence in the cochlea is that water is sloshing, or that actually water is moving back and forth. In order for the water to move back and forth, there needs to be an overflow, and so that's what the round window does. It allows fluid displacement so that incompressible liquid can transmit these displacing waves, because those are going to bend the hair cells, whereas if there wasn't this gross displacement of liquid, the hair cells wouldn't bend. So the book notes briefly that there's a disease that causes overgrowth of the round window. So I just want to mention briefly, they talk about fenestration. So again, fenestration meaning the creation or presence of windows. And so this round window, the lack of of the round window can be solved by this fenestrating surgery. We talked about the fenestration in the context of the blood-brain barrier earlier, so just to mention the word again. Here's a picture of all of that: outer, middle, inner, right? So in the outer ear, the signal is a compression wave in air. In the inner ear, it's still an air-filled space, but the signal is being transduced through the movement of these bones. And then in the middle ear, or the inner ear, sorry, it's now a fluid wave with displacement because of this round window. And here's the cochlea, looks like a snail. This part is a vestibular apparatus. This part is where the organ of corti is. And you see the auditory nerve coming out of there, the vestibular nerve coming out of here. They join to form cranial nerve 8, and that goes then into the brain. So this is what all of that looks like. And we'll talk more about both of these parts next. So here's the organ of corti again in the snail body part of the cochlea. And what I want to emphasize, so there are these different spaces and membranes. What I want to emphasize in particular is these hair cells. So there are outer and inner hair cells. The yellow ones are the outer ones, and the blue ones are the inner ones. They're called inner because they stick to the basilar membrane, the one that moves. They're called outer because they stick to the tectorial membrane, the one that's relatively rigid. And they both are involved in hearing, but they're involved in hearing in different ways. So these hair cells contain cilia, and the cilia are connected together by tip links so that they all move together. And the cilia are arranged by height. And the physical design causes hair cells near the oval window. Those hair cells respond to high frequencies. And the hair cells at the other end respond to low frequencies at the inside of the coil. So what I mean by that is here, high frequencies, low frequencies. Does that make sense? So this is where the tonotopic map is being created. Each set of hair cells differentially has a primary response to a certain frequency range. There's a lot more frequency ranges than there are rods, than there are cones. And so in the case of light, you're transducing all light into a combination of 3 colors. Here, there's a whole array of hair cells that respond to different frequencies. But you can actually just pick a limited number of them and still get a pretty reasonable model of sound by combining them, and that's what is happening with a cochlear implant, because the number of detectors in a cochlear implant is much smaller than the number of different hair cell frequencies that you've got. So there are 3,500 inner hair cells, and 99% of the axons that are going, 99% of the afferents that are going to the brain are connected to these 3,500 inner hair cells. And they're connected in such a way that each axon, or each axon is representing multiple hair cells. I'm sorry, each hair cell is being represented by multiple axons. There are 12,000 outer hair cells, and only 1% of the afferents snaps on these, and they're the opposite. So many hair cells, many afferents to hair cell, many hair cells to afferent. And the logic is kind of like your photopic and scotopic vision. So here, you have a few hair cells and lots of attention paid to them. This is like your scotopic vision when there's plenty of sound. This is mostly involved in amplifying very soft sounds, much like the rods, where it had a many-to-one connection to the bipolar neurons. Remember when we talked about the eye, the rods were pooled together so that many rods, each one of them might just see 1 or 2 photons, but then you get a signal from them all together. That's what's going on in your outer hair cells. Deformation of hair cells, again, opens an ion channel and another part of the body called an insertional plaque. That leads to EPSP, and then they synapse with a bipolar neuron. These bipolar neuron axons are these afferents. And so each bipolar neuron, in this case, is each hair cell serves multiple bipolar neurons, whereas in this case, multiple hair cells serve one bipolar neuron. And then they get in the cochlear nerve. So again, a lot of commonalities to vision. So place code and rate code. One subtle detail here is that both of these are actually going on at the same time. Generally speaking, the cochlea is designed around this place code, meaning different parts of the organ of corti respond to different frequencies. But the lowest frequencies don't work well this way, and they're actually transmitted by a rate code. And that is in part because as the frequencies get very low, we talked about the size of like a middle C on a keyboard, right? It was like 1.3 meters, which is, like this much or something like that. So the reason that in part that these low frequencies are transcoded by rate is because it's very hard on this size scale of the ear to build a detector that will respond differentially to like 6.5 meters versus 6.6 meters. And so the rate code is more efficient in that domain. So here are some graphics of some of this. And so particular region of the basilar membrane is going to be selectively deformed by the incoming sound. That generates a sound distribution in this place map because these receptor cells are connected to certain bipolar neurons which represent a certain part of the frequency spectrum. So perception of timbre. Many sounds, like musical instruments, are made up of a fundamental frequency with overtones or harmonics. And your voice is a good example of that too, if you have any singers in the room. If you're a singer, you talk about what is it called, like a head voice, and then the other one is a body voice. Is that right? You know what I'm talking about? So, do you know what falsetto is? Right? So falsetto is something that actually men and women can both do. But essentially I think singers call it a head voice or head space. What they're doing essentially is removing fundamental frequency and just having the overtones present. And so that's how you create your upper registers versus your lower registers. You can open up the back of your mouth, your throat, with certain exercises, and so I can lower my voice and make it really deep. And then if I close that back part of my throat, my voice gets higher in pitch because some of those fundamental frequencies are lost. Like when we do speech therapy with kids with craniofacial disorders like cleft palates, this kind of thing is important because they have really nasal voices. They don't open up the back of their throats very well. You can teach them some things that will create normalization of the voice. If you think about a musical instrument, a lot of the wind instruments are designed very similarly. Like on a clarinet, there's the button on the bottom that opens up the hole that lowers the opening and closing that hole goes from the upper register to the lower register by adding that fundamental frequency. So this is another example of that Fourier analysis that we talked about last time. The splitting, you could split light apart into a frequency spectrum, and you can say there's a certain amount of light at this frequency and a certain amount of light at this frequency and so on, and that decomposition can then be reconstituted into that perception of light. Same thing happening with sound here, and so you're decomposing this sound into these different frequencies that are present, and the distribution of different frequencies and how they compare to the dominant tone is what creates the timbre of the instrument. So that's what makes a clarinet sound different from a violin when they're playing the same pitch. As noted in the textbook clarinet example, a lot of musical instruments, as well as voices, are characterized by timbre during the attack and the decay, when the sound begins and when the sound ends. Whereas, like if you're trying to tell musical instruments apart, like if you listen to a clarinet and a violin, when they're in the middle of a note, it's really hard to tell which one is which. When they start a note, when they end a note, it's really easy to tell which one is which. And that's a general principle that's true for other kinds of sounds as well. Spatial localization of sounds. And so, as I mentioned, your ears are focal devices. And so just what sounds are relatively loud in your ears tells you where they're located to some extent, but you have some additional tricks to do more sophisticated localization of sound. You use two different tricks for high and low frequency sounds. that the book mentions. So for high frequency sounds, localization is mostly through intensity difference. These sounds are absorbed by the head, and so if sound is coming from this side, it comes directly into this ear, it gets absorbed by the head. The bounced sound that's coming over here is softer because it's bouncing around and losing magnitude as it propagates through space, has a much longer propagation distance than the sound that came in this way. And so for high frequency sounds, localization is through intensity difference. The difference with low frequency sounds is they pass right through the head. And so the sound goes, so like here, if path length determines how loud the sound is, this is the path length for the high frequency sound, and then the path length for the low frequency sound is something like this, right? For the the path length for the high frequency sound on this side and the path length for the high frequency sound on the other side. For the low frequency sound, the path length for the low frequency sound, the path length for the low frequency sound, they're almost the same, right? And so you can't use that technique. And so instead you localize low frequency sounds through phase difference. If you don't know what phase difference means, I can draw you that really quickly. We talked about our sine wave again as a general model of how waves work, right? And this was one period of the sine wave, and it's called it's a wave because it repeats, and so it's the same thing again, right? So the phase means that you can have a sound wave that starts here, or you can have that same sine wave that starts here and does the same thing, but it just hangs out a little bit before, right? So this way, the phase of this is earlier because it started earlier, right? So this is what I mean by phase differences. So you're detecting when the sound hits its peak. And if the sound is only 10 hertz or 20 hertz, so 20 hertz means that it takes a 20th of a second to get this far. So a 20th of a second is 50 milliseconds. And so you might have a phase difference of 5 or 10 milliseconds or something like that, right? You can work with that. But most of your fast neurons fire at about a kilohertz, which is a tenth of a millisecond. And so if the phase difference is much smaller than that, your neurons just can't fire fast enough to register that kind of phase difference. So take a second for this to warm back up. And as it's warming back up then, so this phase coding tells you how low frequencies are localized because the intensity coding doesn't work because they pass through the body. But I do want to mention that very low frequencies are not easily localizable. And your subwoofer in your stereo system, if you have one, is a really good example of this. If you have a home theater system, for instance, you got a subwoofer, it's a little box, right? They tell you to put it behind the sofa or something like that. The way that your hearing works for those very low pitches, those low frequencies, is that you will almost always hear this low frequency in the context of high frequency sounds. What your brain will do is code the place of the low frequency by the high frequency that it's tagged with. And so the reason your subwoofer works is because you've got, like if you have your home theater system, you've got that subwoofer in just one place making the very low frequency sounds. You've got the high frequency speakers distributed around. And so if you want the low frequency to seem like it's coming from over there, you run the subwoofer and the speaker that's over there at an overtone, and your body will think that the sound is coming from over there. And that's like a Gestalt principle essentially. It's a lot less complicated than the idea that there was a low frequency sound over here and its harmonic was being heard over there. That's a more complicated explanation. You go for the simple explanation. Just like it's a more complicated explanation to think of 36 dots in an arrangement instead of a circle, and so you think of a circle. So it's a Gestalt kind of an idea. The pin as differential amplification of sound again, the shape of your ear does also help with localization. And it's kind of optimized for localizations that are important, essentially. You can also localize by a vertical angle, and so there's the picture with the cat in the textbook to do that. Here's a picture of what the phase difference looks like in a different way. And here again, these waves are compressions and rarefactions, and you see how in this particular wave, at this ear, it's a rarefaction, but at this ear it's a compression. And in contrast here, both ears are in compression. And here what they're doing is, because there's a difference, you can tell the wave is moving this way. But since there's no difference, if they stay synchronized, it tells you the wave is not moving across the body. So here you're localizing left to right versus front to back. Here's the auditory pathway. I don't want to go into gory detail because of the content that's in this book. We're not going to talk about these structures in detail, but I want to kind of identify the concept of how these pathways look. Like we talked about the visual pathway, and the visual pathway is from the optic nerve to the optic chiasm to the optic tract into the lateral geniculate nucleus to the cortex, and so it was essentially receptor, nerve, thalamus, cortex. It's a similar kind of an organization here. And I don't know, I told you I wasn't good in mnemonics. The one that was used in my neuroanatomy class was NC-SLIMA, so NC-SLIMA. Somehow I remember that one. So it goes from the auditory nerve to the cochlear nucleus, and the cochlear nucleus is in the brainstem, to the superior olivary complex, which is again in the brainstem, to the inferior colliculus. And I don't think I mentioned the superior colliculus in detail, but these colliculi are involved in really primitive processing of information. And so like the ability to respond by orienting your head to sound is a brainstem function. The superior colliculus is part of a pathway called the tectospinal tract, and what it does is allow you to move your eyes in response to your head rotating. Really, really primitive brain reflex. And so, this part of the pathway is important for these primitive brain reflexes. Then it follows this thing called the lateral lemniscus, which is essentially a bundle of fibers, up to the medial geniculate nucleus. And here again is a kind of analogy to vision. So vision passed through the superior colliculus, and the inferior colliculus is in sound. Vision passed through the lateral geniculate nucleus. The medial geniculate nucleus is involved in hearing. And then it goes to the auditory cortex and the temporal lobe. So consistent with vision, temporal plus processing is an important concept again. We talked about the where and what streams in vision, right? And so there was a dorsal stream that went over the top that was involved in the where information, like place coding in vision, and then the ventral stream that was the what, or the semantic or meaning content of the vision. There's a where and what stream for hearing as well. And once again, the where stream is dorsal, and the what stream is ventral. So same kind of concept, different pathways. And here you can see that in the brain imaging. So really briefly about music and audition. I noted previously that right hemispheric activation in untrained individuals shifts to left hemisphere activation in musicians. And that's actually in proportion to experience. There also tends to be more prefrontal activation, particularly on the left. All this suggests that there's overlap between music interpretation and trained individuals in language functions. And language is really a core function of the auditory system. So the auditory structures on the left hemisphere in particular, in most people, are really important because language is a really, really important reason why we hear. And a lot of other things that we do are modeled off of language. And it's arguable that maybe you even go so far as to argue that if Noam Chomsky made this argument that language has a deep structure and a surface structure, and there are ways in which all languages are the same, and the reason the way that all languages have these similar features is because the brain has evolved to process language in that fashion. For instance, like nouns and verbs, like a fundamental construct. And so any language that you deal with will have nouns and verbs. It's arguable that music also, although it's very different in different cultures, has features that are based on how we hear sounds to hear language. And sounds that can be interpreted using our language structures are likely to be likely to be something you can make into pleasing music, and sounds that we can interpret in this way are likely to be less pleasing as music, or more likely to be noise, essentially. Any question about hearing before we move on? The vestibular system. So common architecture with audition, and that's important. So the ear and the cochlear complex and everything is used for vestibular functions as well as hearing. The vestibular hardware is essentially an acceleration detection scheme. And so what it does is detect linear and angular acceleration. And so what I mean by linear acceleration is moving in space in a straight line, to the side, to the back or the front, up or down. And then what I mean by angular rotation is rotating in 3 planes. You can think of those 3 planes as pitch and roll and yaw, or you can think of them as sagittal, coronal, and horizontal planes. So for instance, in the sagittal plane, the rotation is this rotation. That's the same one that we call pitch. In the coronal plane, the rotation is this rotation. It's the same one that we call roll. In the horizontal plane, it's this rotation. It's the same one that we call yaw. And so there are 3 dimensions. There are 3 angles. So if you want the position and orientation of an object in space, you need 6 dimensions, right? You need its x, y, and z, for instance, in roll, pitch, and yaw. So there are 3 angular orientations and 3 linear orientations. Rotation of fluid in these semicircular canals. You see that basically the structure makes sense. You've got 3 semicircular canals. Each one is one of those planes. So you have a semicircular canal in the sagittal plane. You have a semicircular canal in the coronal plane. You have a semicircular canal in the horizontal plane. And so the motion of the fluid in each one gives you information about angular momentum, angular acceleration in those planes. And there's a cupula and ampulla construction, and again, hair cells, the bending of the hair cells, again, causes an EPSP. So it works in a similar fashion to other senses. And the vestibular sacs are kind of conceptually similar. They're circular organs. One detects up-down and the other detects in-plane acceleration, meaning in the horizontal plane. So you have this acceleration and then this one in the horizontal plane. In essence, linear accelerations cause a shear of the cilia. And so if the cilia is like this and you accelerate, its shear is moving, it's causing a shear force here. And it again results in a perception of acceleration. They're called otolithic organs because what allows for that shearing motion is this structure that has these crystals, and the weight of the crystals causes a displacement between the heavy surface with the crystals and the light surface in the other membrane. Here's a picture of that. So this otolithic membrane is the heavy one that has the crystals, and it moves in comparison to the lower structure. And so because the structure is heavy, it moves in the acceleration, that bends these hair cells, and that triggers an EPSP. And here you see the utricle for horizontal plane and the saccule. So I want to mention really briefly 2 things that I mentioned kind of more briefly in the book: dizziness and vertigo. Vertigo is an important concept in understanding the vestibular system, and vertigo, when it's well defined, is usually a fairly specific vestibular symptom. And essentially what it is an acceleration hallucination. So you have the appearance of rotating or translating, right? So for instance, if you have an illusion of rotating in this plane, like you feel like your body's spinning like you're doing a somersault, then that means that sagittal semicircular canal is dysfunctional. If you have a rotation in a different plane, it means that one of the other semicircular canals is dysfunctional. So that's vertigo, this specific rotational sensation. as opposed to non-vertiginal dizziness, so just general dizziness where there's not this uniplanar kind of characteristic to it. That can be vestibular, that's not necessarily vestibular. If it's uniplanar rotation, it's usually a vestibular symptom. I won't go into a lot of details about the vestibular pathways, but I do want to emphasize again, there's a cranial nerve. That cranial nerve has a ganglion with bipolar neuron bodies, and then those axon synapse, mostly in the medulla. This is slightly different. So there's this ganglion that's external versus in the auditory cortex, that first synapse is happening inside the brainstem. So these vestibular axons from the ganglia, I'm sorry, wait, I didn't say that right. So the difference here is that the the difference here is that the ganglion for audition is right here, and then exiting the cochlea is the auditory nerve. The difference is that in the case of the vestibular system, there's this external ganglion where the bipolar bodies live. So the vestibular axons, though, they mostly go to the medulla, which includes vestibular nuclei, like there are cochlear nuclei. They also go directly to the cerebellum, and then they project from the nuclei in the medulla to a variety of places, also the cerebellum, the spinal cord, the pons, other parts of the medulla, the cortex. The spinal cord is important because you need to be able to react very quickly to vestibular signals in order to maintain station and gait, like to be able to walk and stand, for instance. And so you need to be able to do this without a lot of higher order processing, and so it can bounce directly back to the spinal cord to adjust the body, like to adjust muscle tone, to maintain standing position, for instance. So any questions about the vestibular system? We didn't talk about that in a lot of detail. Again, a lot of the concepts are very similar to the other systems. So the somatosensation, or your touch sensation, there are actually several different somatic sensations. There actually is a difference between fine touch, which is like the kind of touch where you can discriminate 2 points on the surface of your hand, and gross or deep touch. And there's actually some interesting evidence that deep touch may have limbic triggers, and this may be part of why deep tissue massage is so relaxing. It may also be part of why things like weighted blankets and weighted vests work as sensory interventions. So we have a golden retriever at home, and I don't know if any of you have seen these, but there are these weighted, there are these vests, these compression vests that dogs wear, and it keeps them calm during thunderstorms. Some of them get wound up during thunderstorms. That kind of stuff may be related to deep touch rather than fine touch. There are also separate sensations for temperature, pain, vibration, and proprioception, which is the body position sense. This is the body position sense, this is the body motion sense. The reason I'm bringing this up is I do want to emphasize that these are different sensations. If you do more graduate neuroanatomy, what you'll understand is that these pathways are different. And so you'll see like spinal lesions, for instance, that'll affect some, but not all of these. Or they'll affect some of these things in one part of the body and other things in other parts of the body. What I want to emphasize, though, is like you could imagine, for instance, that your gross touch, your deep touch, was just a really high level of stimulation of lots of your fine touch integrated together. That's not the way it works. Similarly, you're not generating a vibration sense because there's a on and off stimulation of fine touch. It's actually a separate sensation. So they're more or less discrete sensory modalities, and they're not computed or extracted one from the other in the way that information is perceived from vision. So I do want to say that these are, again, many of these are very sensitive. One example is that you can perceive roughness on pretty close to a 1 micrometer kind of scale, and that's 10 to the minus 6 meters. So it's like 100th of a human hair, something like that. So like if you think about like like if I give you two pieces of paper and you rub your finger across it, you can tell me which one is smoother. The size scale of those variations on the paper surface is very, very, very small. Like 1 micron is like 50% larger than the wavelength of red light. That's really small. So it's a very sensitive sensation, fine touch, especially in your fingertips, for instance, and your lips and a few other parts of your bodies. In understanding the somatic sensations, you need to understand the skin. And there are two kinds of skin. And hairy skin may have more or less hair. It is important to emphasize, like some people, for instance, like some people don't grow facial hair, like some men don't grow facial hair. It's still hairy skin, right? As opposed to glabrous skin. So your glabrous skin, the best example of glabrous skin is your palms, right? So your palms are made of glabrous skin, the backs of your hands, whether or not they're hairy, are made of hairy skin. They are slightly different. Hairy skin contains free nerve endings and these ruffini corpuscles that respond to indentation, and these Pacinian corpuscles that respond to vibration. Again, discrete sensors for discrete sensory systems. The glabrous skin contains some additional receptors, Merkel's discs and Meissner's corpuscles, that allow for some enhanced sensations in certain domains. So, fine touch. Fine touch is a really important touch sensation. It's caused by mechanical, elastic deformation of the skin, triggering mechanoreceptors. It's important to emphasize that fine touch is touch that is in response to sensation that is below the threshold of injury. That's why I mentioned this elastic and not plastic deformation. And so, little, relatively gentle stimuli. The touch sensations trigger receptors in the skin, and then they travel along sensory nerves from the skin to the spinal cord. There's a dermatome distribution in the spinal cord, and so we talked about the thoracic, the cervical, thoracic, lumbar, and sacral spine, right? And so each part of the spine each root of the spine covers a different part of the body. That's what the dermatome map means. And so, for instance, this purple part is S1. It's the first sacral root, and this blue part above it is the last lumbar root. Or I think actually the last lumbar root is over here. But so the touch sensations enter the spine in a dermatomal distribution, and these dermatomes have different sensitivities. And 2-point touch is a really common metric. And so, for instance, what that means is, my fingers are really gross stimuli, they're big, right? But if I touch my palm with 2 fingers, I can tell that I'm being touched by 2 fingers. Even if I use something sharp, like a toothpick, it can be very close, like 2 millimeters on my fingertip. If you put your hand behind your back, for instance, and you touch the small of your back with 2 fingers that are close together like this, you won't be able to tell that it's 2 fingers. 30 to 40 millimeters is on the order of 1.5 inches, so like this much. Like that's the kind of distance scale that you need to touch your back with 2 fingers to know that they're 2 fingers instead of 1. So 30 to 40 millimeters, like this much, in places like the back. 2 to 4 millimeters in places like the fingertips. And what goes along with that is the sensory homunculus. This is a male sensory homunculus. I was looking kind of in a hurry and I couldn't find the female one quickly. But the idea is very similar. The idea of this, you've seen this kind of picture before, right? And there's a sensory representation and sensory cortex. The idea of this is it's differential with different parts of the body. So notice how the hands of the homunculus are really big. The reason the hands are big in this picture is because for the amount of skin surface area, the hands take up a lot of cortex. The fingers take up a lot of cortex. You look at, in comparison, the torso. This is the front and the back of the torso. The whole thing is this. Your fingers are all of this. So certain parts of the body have a much have a much larger representation in the sensory cortex. Those are your fingertips, your lips, and your toes to a lesser extent, your genitals, and a few other things that are more represented. Things like your back, your legs are relatively underrepresented for your touch sense. And that makes sense, right? Like you figure out, like you're not trying to figure out what an object is by rolling it across your calf, you're rolling it across your fingertips. And so you need a lot of representation here. Temperature sensitivity. So thermal receptors are differentiated actually, interestingly, into warm and cold receptors, so it's a two-factor kind of model. Meaning that it's not one receptor that detects a range of temperatures, it's warm and cold. And in particular, it's warm and cold with respect to your body. So I do want to mention in passing that the warm detectors are deep in the skin and they're unmyelinated, meaning they travel slowly. The cold detectors are near the skin surface, they're thinly myelinated. When we talk about neurological diseases, MS, for instance, attacks myelinated fibers. It's going to affect these fibers, it's not going to affect these fibers. So it's going to affect in principle, it could affect your cold sensitivity, but not your warm sensitivity. There are a handful of different sensors, and each one detects a range of temperatures. So here's 0 to 50 something. And that's the general range. You can detect cold from about 0 to about 50. And so thermal detectors are only designed to detect this smaller window of non-damaging range of temperatures. This is similar to how so your eyes detect a certain range of light brightness, right? And a lot more brightness than that could potentially damage your eyes. Your fine touch is detecting non-damaging skin touches. Your temperature sensitivity is for non-damaging temperatures. The differential response between 50 degrees Celsius and 500 degrees Celsius, which might be like an oven or something like that, well, oven maybe 250 or something, the difference is not the temperature sense system, it's the pain system. Because your temperature system is not designed to detect damaging levels of temperature. Some receptors can be artificially stimulated, and so some of these are also chemoreceptors. And so there are some chemicals that feel hot or cold for that reason. Talking about pain next, these are mechanoreceptors. They sense more intense pressures. They sense, and they're free nerve endings that detect things like extreme heat, acid, certain chemicals. So some of these are detecting damage to the skin, although a lot of it is minor damage that can be easily healed. It's detecting damage as opposed to things like an elastic deformation, like a fine touch deformation. So like what I mean by that is I'm touching my skin here, my skin is deforming, right? Like if you touch your fingertip, it goes down. So that's the deformation. The skin caves in, but it pops right back, right? If I touch much harder and I leave a mark, that's a pain receptor that I'm stimulating. There are a third type of pain receptors that detect specific inflammatory chemicals as well. One thing to know about pain is that these sensors are poorly localizing, and so you can't discriminate, for instance, that you're being poked in two places 2 millimeters apart on your finger versus one place. Your pain system's not built that way. You just know your finger hurts. These somatosensory pathways, generally speaking, again, they're going through these nerves and ultimately up to the cortex. There are some similarities here again. So here, for sensory sensations, there's a ganglion in the root, right? As opposed to the motor entry into the spinal cord, where there's no external ganglion. So there's a ganglion and a synapse, and then the neuron goes up all the way to the brain. So it goes from the dorsal, it goes in from the root ganglion into the spine, and depending on what kind of sensation, it goes to different places. So like your fine touch goes into these dorsal columns, your pain and temperature go to spinothalamic tract, that goes up over here. One thing that's important about that is I mentioned that with these spinal conditions, you'll have some parts of the body affected one way and some parts affected another way. So the dorsal columns cross or decussate up here in the brainstem. The pain decussates immediately, and so that's why you would have one symptom on the left side of your body and the other symptom on the right side of your body. But again, they go to the thalamus as a relay station, and also for processing, and then to the cortex. And again, at the cortical level, it's all contralateral. Remember that concept? So the dorsal column crosses up here. The spinal thalamic pain column crosses immediately. They all end up on the opposite side of the body. So if this is the left hemisphere in this picture, it's handling the right side of the body. And there are three components to pain that I don't want to get into too much detail for, but I do want to mention here in this concept that the book talks about. One thing that's important is that there's no such thing as real and fake pain in a meaningful way that we can currently identify. If you're experiencing pain, you're experiencing pain. In my mind as a psychologist, it's all real. But what's important to know about pain is it can be driven by a sensory sensation. It can also be modulated by the brain, both in the short term and in the long term. So pain is interpreted differently. For instance, if you walk out the door of the classroom and it's gusty outside, then you might find that gusty wind aversive. But if you're driving with the top down and you're enjoying the open air, you might find that same stimulus non-aversive. So you can turn pain on and off depending on the context. And then there are also longer term emotional potentiation and attenuation of pain. And so this is why, for instance, like the Cymbalta commercial that says the depression hurts. So emotional changes can trigger changes in modulation of pain. And so the same spinal input of pain, the same sensory input in the skin leads to these different responses based on not only the sensation and how that's interpreted, but also these other modulatory roles. And some pain can occur starting up in the brain, even though there's no signal from the body. So we have about 10 minutes to talk about the other senses, smell and hearing. I'll try to go over them. Think about questions. If we want to talk about these more tomorrow, next week, we can do that. And I'll try to find some exercises perhaps also. Let me talk about gustation, so your sense of taste. The most important thing to know about your sense of taste is definitely that it is limited to some specific tastes. So in contrast to vision, hearing, and touch, gustation and olfaction are primarily chemical senses. We talked about how some of these other sensors can sense chemicals. This is all chemical all the time. They're both closely related. Gustation is specifically these 5 tastes that you have in your mouth, primarily on your tongue, but also on your palate and your larynx. And so there's bitter, sour, sweet, salty, and the umami or glutamate sensitivity. And we all have these 5 sensations that are distributed in different parts of the tongue and are different kinds of receptors that respond to different kinds of chemicals. And these are it. Everything else about the way food tastes is smell-driven and not taste-driven. And that's a really important concept. So where you can think about this to help you remember this is what food tastes like when you have a cold, which is it tastes bad, right? And that's because you're not smelling, because you have a cold. You're just relying on these 5 tastes. So, like, you have 2 fruits, like you have a tangerine and a nectarine or something like that. They're both sour, they're both sweet. It's not your taste that's primarily telling you which one is which, it's your sense of smell. Another real common situation where this comes up is, I showed you the picture of the brain many times in the course of the class. If you remember, the olfactory bulbs sit at the bottom of the brain, between the brain and the skull. It's really common in head injuries to bump the olfactory bulbs on the skull, and that causes a loss of sense of smell. So lots of people will come to a brain injury clinic and tell you food doesn't taste good. They have to engage in mechanical eating, meaning they're not really hungry, food doesn't taste good, they don't want to eat it, but they know that they need 1,800 calories a day, and so they make themselves eat a certain amount of food at dinner time even though the food tastes terrible. because they don't have a sense of smell, again, and so that's really removing the pleasure from the food. I want to mention in passing that monosodium glutamate triggers the umami sensation of taste, but there's a lot of misunderstanding about this. Glutamic acid exists in a lot of natural forms. Makes sense, that's why you've got this receptor. And so there's a wide variety of food. Chicken, eggs, potatoes, tomatoes, soy. Glutamic acid occurs in lots of things. And so these things are all triggering that umami taste. Although, if you put monosodium glutamate in something that has a lot of glutamic acid, you can taste that sensation really strongly. And so if you put MSG on something, you get a really strong sensation of what MSG tastes like. But that savory kind of sensation that's hard to put your finger on, that applies to potatoes and tomatoes, that's in part MSG, or glutamic acid. Because MSG, again, is monosodium glutamate, glutamic acid plus sodium, right? So I want to mention that the glutamic acid is actually in a lot of food. Gustation, so your sense of taste again, 10,000 taste buds. They're mostly organized on these papillae on the tongue, these surface protrusions. But there are taste buds, as I mentioned, in these other places, the palate, the pharynx, the larynx. Each taste bud consists of 20 to 50 receptor cells. They only last a few days. And then the taste buds project cilia into the saliva for chemoreception. And so the chemoreception happens in this fluid environment. They synapse with a bipolar neuron. Again, a very similar story. Again, like the other senses minus vision, it's excitatory. And then these axons project into the brain. And they actually project through 3 different cranial nerves, 7, 9, and 10. So here's a picture of that. You've got these taste receptors. There's these papillae that draw in saliva, that present the saliva to the taste buds. The chemical response happens. These afferent axons then project through cranial nerves into the brain. The salty taste is triggered by a sodium channel, or is a sodium channel rather. But it's actually triggered by a variety of cations or positive ions. Remember, it's Na plus Cl minus. So the Na is a cation. The Cl is an anion. Important dietary concept. So if you've seen low sodium salt, which might sound like an oxymoron, potassium chloride is also a salt. It also tastes salty. So the way that low sodium salt works is that it's a mix of potassium and sodium chloride. It's actually potentially good for you in some sense because you need potassium, and so you're getting more potassium and less sodium. And so that's something you can do for people with high blood pressure who need less salt in their diet. The sour receptor responds to the hydrogen ions and acids. The bitterness receptor are a bunch of different receptors that respond to specific plant alkaloids. And these bitter tastes are probably primarily designed to tell us about foods that we should not be eating. Although we actually have a lot of learned responses to bitter tastes that we like the hops in beer. And so there are bitter tastes that we view positively. The book talks about how bitters are usually aversive, but there are lots of things where we actually do kind of like them. But a lot of those things fall into this sort of learned taste category. They're not stuff you find naturally pleasant. Sweetness, specialized for sugars like glucose and fructose. One interesting thing is that aspartame will trigger this as well. And so there's some overlap. Some of these chemicals are very similar. Like in the Seville orange, there's just a very small difference between something that triggers the sour and sweet receptors. There's also some limited evidence that there's a separate chemical system for detecting fatty acids in addition to the 5 tastes that I mentioned. And that's an adaptation for scarce food resources. When food is not available, you want to be able to detect fat because it's a trigger for high calorie food, which will keep you alive. It's also potentially a problem because if we're adapted to crave things like fats and sweets, we don't live in an environment where food is scarce. We live in an environment where there's entirely too much fat and too much sweet. The gustatory pathway conceptually is similar in some ways. It comes in via these cranial nerves. There's a big long nucleus called the nucleus of the solitary tract, or the nucleus solitarius. And it's a big long nerve nucleus because it synapses with a bunch of nerves entering the brainstem in different places. But then it projects in a different fashion. Your sense of taste projects to the hypothalamus, to the amygdala, to the thalamus, and then ultimately also to the cortex. But the cortical responses to taste are probably much less important than the cortical responses to other things like vision. So your sense of smell, generally speaking, it is actually very important, although we use it less than animals. The book offers this interesting example of how maybe that's because we don't put our nose to the ground as much as animals. It's your sense of smell, it's sensitivity to a variety of volatile compounds, meaning compounds that will transport in air. And they're usually lipid-soluble organics. But what's interesting is why some lipid-soluble organics smell very strongly, and some are essentially undetectable by our sense of smell. It contains 6 million receptor cells that are in an epithelium, a membrane that's positioned up in your nose so that not all the air goes there. 339 different kinds of receptors, about a third as many as in mice. So there is actually some evidence for the idea that there is actually more sensitive smell in other creatures, more sophisticated smell, but it's also that we don't use it behaviorally. Our resolution is something like 10,000 different smells compared to the 2 or 3 million colors that we can detect. And it's an activation, it's a patterned activation, meaning each kind of odorant stimulates multiple cells. There's some things that are different about smell than the other senses. So the olfactory receptor is metabotropic. All these other receptors we've been talking about are primarily ionotropic. So this is an important difference, meaning this is a slow and diffuse effect. Each olfactory nerve receptor is actually a bipolar neuron. So there isn't a second layer of a bipolar neuron. And the axon projects directly at the olfactory bulb. And then it synapses and projects with a heavy emphasis on the lateral limbic circuit, which handles emotional learning, and the hypothalamus, which handles these motivated 4F behaviors. What's really important about this is the idea that olfaction is really hardwired into basic emotional motivational responses. And so you think about it, like the Marcel Proust thing in the book, smells can trigger very strong emotional responses. Your brain is wired that way. There's a similar system for the vomeronasal organ in creatures that have them. This is the pheromonal system. It's a hardwiring into these emotional and motivated behavior centers of the brain. So here's a picture of that. Again, the amygdala for emotional learning, projections to the orbitofrontal cortex, which is involved in emotional self-regulation, the hypothalamus, which is involved in the 4Fs. These structures are all kind of direct recipients of smell. And here's a picture of what that looks like at a cellular level. So what's important to know about this is a really direct hardwired projection right into some emotional parts of the brain, meaning you have an immediate, even though it's a metabotropic receptor that's slow, you have a very immediate emotional response. All right, so we will